This is week 1 of our energetic Earth, and in this first week we have to deal with some very important and crucial preliminary issues. Week 1 is all about solar energy, and that's essential because solar energy is really the thing that produces most of the dramatic and exciting energetic events on the surface of the Earth. So it's essential that we come to grips with this basic concept of solar energy and its input. One of the things that's perhaps most interesting about solar energy is it's not so much that it is coming from the sun and not so much that it's fairly uniform because the Earth's orbit is a fairly uniform distance from the sun, but there's a geometric idea that underlies the Earth's response that's just critical for us to begin to understand. If we think of a beam of light, like the one that's shown here that's coming in from the sun, and it hits on a plate, this plate could be a receiving part of the Earth's surface. It could even be something like a solar collector that's specifically designed to collect it. But if we think about that, this plate that's shown here is perpendicular to the rays which are coming in left to right, and this is up and down, so it's at right angles to that. And the solar intensity we can imagine as being maximum at this particular point because all of the beam is collected. But if we think about rotating that plate to a different angle, in this case to 45 degrees, the implication of that is that a plate of finite size will now allow some of the light to escape on either side that was formerly caught by the plate. This means, by implication, that the average intensity over the surface of the plate is reduced considerably. It's reduced by this amount that we no longer catch. And that means that the average intensity has gone down as a direct function of the orientation of the surface. As simple and as straightforward as that idea is, it has amazingly important implications for the way the Earth works. First of all, in any given area, there's clearly going to be a difference between the angles that the surfaces have relative to the angle that the sun is coming in at. So we get a local effect, but we get very significant global effects as well. Parts of the Earth are clearly oriented more close to perpendicular, and parts are actually closer to parallel. And if we move this plate to a parallel position, we can see that now the surface of the plate receives almost no energy at all. And in fact, the only shadow effect that we would have on our fictional wall here is associated with the width of this plate. And so that is going to give us a minimum now of solar energy intensity on a per unit area basis on this plate. And from this explanation, we're going to be able to understand not only the issue of why it gets colder as we move away from the equator towards the poles, but we're going to understand the way seasons work as well. So this is the missed energy in this particular case, and clearly it's at a fairly high level. If we think of that 45-degree angle again, one of the other ways that we can imagine thinking about the idea of the plate is to think of the fact that you would have to extend the width of the plate in order to be able to capture the full amount, which is yet another way of saying that the average intensity has gone down at this particular point, the average intensity per unit area. If we were to plot this, we get a very consistent and fairly easy generalized plot with a maximum on the plate or the receiving surface is at right angles to the incoming solar radiation, and it decreases quite rapidly towards a value of 0 when the plate or for the receiving surface is oriented parallel to the incoming rays of the sun. There's one other way that we can think about this, which is extremely helpful for the surface of the Earth as well. And that's if we go back to this 45-degree angle for the plate. We can imagine that we put another perpendicular plate, but this one's smaller. And what we can see easily is that this plate here, the green one in this particular case, will collect the same energy that this longer blue one will have. So the average intensity will be greater on this one, but the total amount of energy that these two plates collect is in fact the same. The same amount of energy escapes, and so the net amount of energy that each plate receives is the same. And what this gives us the idea of is that the projected area of the plate is what really matters. Not so much its actual area, but in fact we can think of that projected area as being that component which actually is the part that's effective for receiving the solar radiation. When we think about the Earth, we have a geometric effect really coming up in very significant ways. The first is, if we think about the sphere of the Earth in this particular case, we get this direct line of illumination marking the night on one side and the day on the other side. And this day-night light line divides the Earth into two. And so the average intensity over the whole Earth is clearly reduced by 2 as a result of this day-night effect. But because the Earth's surface is spherical and not simply a disk, it means that the total area on this illuminated surface is in fact twice the area of the equivalent disk. In fact, the same shadow, the same circular shadow, would be formed even if the Earth had been a disk in space. But the implications of this is that the total projected area of the Earth determines the total energy input, but the average area over the surface of the Earth is reduced by a factor of 4. 1/2 as a result of this day-night separation, and another half as a result of this circular or spherical shape. The other implication that's extremely important to understand with respect to this is that orientation factor that we just considered. Some parts of the Earth's surface are perpendicular to the beam, some parts of the Earth's surface are parallel to the beam. And if, as we've shown here, the axis of rotation with the north and the south poles is aligned with this day-night line, then each part of the Earth will receive the same daylight, the same hours of day and night. As the Earth rotates, each part will come into the same dawn and sunset that all other parts will receive. What is perhaps the most dramatic thing about the Earth, though, is that not only does the Earth rotate on its axis, but this axis is not perpendicular to the orbital plane. The axis is in fact tilted by 23.5 degrees. And this 23.5 degrees is a fairly constant distance or constant angular separation. And of course, because the Earth's rotational inertia, this angle, this axis representing the north-south line, doesn't change as the Earth rotates around the sun. But the important thing at the moment to realize is the day-night line now is no longer aligned in some orientations with the axis of the Earth's rotation. And this gives us a decided bias. For the picture that's shown here, the south side of the Earth is pointed a little bit more towards the sun, and the north side is pointed away from the sun. This is still the axis of rotation. So in this orientation, this northern part of the Earth will never receive any light at all, whereas the southern part of the Earth will receive continual illumination. And so this is going to be our explanation for how seasons take place. If we think of the Earth's orbit as a whole, we can think of several different positions of the Earth representing typical or extreme conditions over the typical annual cycle. This is the one we were just showing. This is the summer from the southern hemisphere, and the tilt of the Earth is biased towards that southern portion. The northern half is receiving a deficit of energy, and the southern portion is receiving an excess of energy. The one thing that we should probably emphasize at this stage in the course, though, is that this excess of energy that is received in this perpendicular region versus the polar region isn't as simple as it first sounds. In fact, the Earth has remarkably important energy redistribution mechanisms, and we'll be learning about those in subsequent weeks in this course as we think about the dynamic atmosphere and oceans that produce such an enormous energy transfer to partly adjust the Earth for this bias. As the Earth rotates to its next position, in this case we're imagining it reaching its vernal or its spring equinox. In this particular thing, you can imagine that this Earth axis is now in the plane that's in fact perpendicular to this orbit of rotation. And so now the day-night line and the Earth's axis of rotation will be coincident. They will be in the same plane. As the Earth moves to its new location here, the axis is always moving parallel to what it was before, but its orientation from the sun now is reversed. Here the bias is towards the south and away from the north. Now the bias is towards the north and away from the south. And this, of course, produces the conditions of the northern hemisphere summer or the southern hemisphere winter. And this is taking place typically around the 21st or 22nd or 23rd of June. The reason why these days shift a little bit from year to year is because the leap year is not added in a uniform fashion. We sort of accumulate 4 quarter days and then add a day all at once, and as a result of that we get a bit of a shift in that occurrence of these key days. There is a second equinox that happens on the opposite side from the first equinox, and that occurs when the Earth axis again is aligned in that perpendicular plane to the Earth's rotational orbit. One of the things that's perhaps interesting to note at this point as well is that the distances that the Earth is from the Sun are a little bit different in these different orientations. In fact, the Earth's orbit is slightly elliptical. It comes to a closest approach at about 147 million kilometers. That takes place around the end of December. It's actually in early January, but it's closely aligned with this northern hemisphere winter solstice, and it's furthest away in early July. As a result of being further away, in fact, the Earth travels a little bit more slowly. As a result of being closer, the gravitational potential energy means it moves a bit faster. And so the Earth goes a little bit faster over this portion of the alignment than it does over this portion. But that's partly compensated by the fact that the solar energy is actually more intense where it's closer, and so the southern hemisphere receives a slightly shorter but slightly more intense summer than the northern hemisphere. We can point these things out a little bit more accurately if we think about lines of latitude. Lines of latitude are these parallel circles that are formed by cutting the Earth perpendicular to that axis of rotation at different angles. And so we have the equator at 0 degrees latitude, and if we go 30 degrees north or south, we get characteristic latitudinal lines. And of course, at 90 degrees, we have the North and the South Pole. These areas that represent the degrees of being 23.5 degrees north or south are very important lines of latitude, and these are called the Tropic of Cancer and the Tropic of Capricorn. And why they play such a significant role is precisely because of these geometric effects. Again, we can emphasize this by thinking about the angle that the Sun makes at solar noon. That's when the Sun is highest in the sky on a day like, in this case, at one of the equinoxes. The equator, the Sun will be directly overhead. It's in direct alignment with this, and so the Sun reaches a total angle of 90 degrees from the horizon, or it's right at the zenith of the sky, at the highest point. If we go to this Tropic of Cancer, or the Tropic of Capricorn, the Sun will have reached an angle of about 66.5 degrees away from the horizontal, and if we move towards the pole, the Sun's rays will be coming in parallel. Clearly, the intensity of solar radiation is greatest in the equator in this particular configuration and is almost zero at the poles. It's only because of the slight variation of orientations of surface that in fact this captures some sunlight at all. In the biased position, in this case in the northern summer, we have the 23.5 degree angle being formed between the day-night line and this Earth's axis of rotation. And this means that even at the North Pole, the Sun now is a considerable way above the horizon at 23.5 degrees. And in fact, the 90 degree Sun, where the Sun reaches the zenith at the top of the sky, will be in the Tropic of Cancer at 23.5 degrees north. Whereas at this Antarctic Circle location, at this 66.5 degrees, that marks the line or the zone here of perpetual darkness, and the land of the midnight sun is taking place really in this whole area that's north of the Arctic Circle. This is an area where the sun would vary a little bit over the horizon, but in fact would never fully set. In the winter, the conditions are really exactly the same, of course, with reversed hemispherical polarity. What we have here is that the southern hemisphere has got the bias. It now receives this area of the midnight sun. The northern hemisphere is in perpetual darkness, and as a result of that, the solar energy inputs are extraordinarily varied. In the northern hemisphere, this area is going to be progressively cooled as it receives very little energy from the sun, but is still radiating energy out into space, whereas this area receives the summer conditions characteristic of gradual warming. The 90-degree overhead sun now has migrated as far south as this Tropic of Capricorn. And you can have a look on any globe or any map and get a sense of where that location is. This is a fascinating set of areas and interactions. If you want to learn a little bit more about this, there's a couple great websites with terrific animations, and we recommend that you look at those. What we need to understand next is a little bit more about the way the sun angle changes through the day and the implications that this has for the energy received on the surface of the Earth.